The first one you had x plus y, x minus y. This was a special case. If you remembered it, you could go straight to the answer of x squared minus y squared. Second one, also a special case, as was the third one, a plus 4, a minus 4. Whether you foiled or remembered it, you should have gotten a squared minus 16. And number 3, 2x minus 3y, 2x plus 3y, 4x squared minus 9y squared. All right? So hopefully you'll remember that special case. When it's a plus minus of the same thing, your middle terms will always cancel. They will always cancel. The next two were also special cases, 5x minus 2, 5x minus 2. The first one is the first one squared, 25x squared. The last one is the last one squared, 4. And then the middle one is the 2 multiplied together and doubled. 5 times 2 is 10, doubled is 20. So you should have gotten 25x squared minus 20x plus 4. Special case for number 5 too. 3x plus 5z, 3x plus 5z. The first one is the first one squared, 9x squared. The last one is the last one squared, 25z squared. And the center is the 2 multiplied and doubled. 3 times 5 is 15. 15 doubled is 30. So whether you foiled it, or whether you remembered your special case, you should have gotten those answers. Any questions on those 5? As bell work reminded you, we have special patterns. So in the last chapter, we looked at special patterns when you were multiplying, but this whole chapter has been about factoring, all right? And so now we are going to learn to recognize special patterns from the other direction, all right? So hopefully as you were doing your bell work, even if you didn't remember it at first, by the third one, hopefully you remembered you had a special pattern because the same thing was happening. It's a little more difficult to recognize these special patterns when you're factoring, because if you don't remember them, you kind of have to think about the fact the center is 0 for the first pattern. All right, the last one you can actually do without the pattern, but this one you kind of need to remember this pattern. And so this is the first special case that we're doing for factoring, and it is the a plus b, a minus b setting. So they remind you of it here. We have x plus y, x minus y. We'll do that with a little bit different color there. So x plus y and x minus y. They are the same exact terms, but it's plus minus. And so every single time you FOIL, you're going to get some perfect square right here, some perfect square right here, and it will always, always, always be minus in the center. And so now what we're going to do is we are going to recognize this second piece of it over here, because we're going to go from this direction that way. We're going to factor it. So you're going to be given the perfect square, the difference of 2 perfect squares, and we are going to factor it back to the plus minus. All right? And so that's what this down here at the very bottom says, factoring the difference of squares. So that's what this is actually called. You'll hear that term, difference of squares. Difference meaning subtraction, squares meaning they're a perfect square. All right? Difference of squares. So if you start with 2 things that have perfect square roots and you are subtracting them, you can always factor them using the square root of the first plus and minus the square root of the second. All right? And so this is actually one of your easiest factorings that you will do if you remember the special case. All right? If you remember the special case. What you have to keep in mind is that middle term is 0. So what happens is they zero out. All right? They zero out, which is what happened on your bell work for your first 3. So let's look at these examples here, the first examples. Factor x squared minus 49. Now, everything that we've done to this point has been 3 terms. You've looked at the last term, factors of the last term that add up to get to the center. The problem here is we don't have a center. Technically, it's adding up to 0. So this, if you don't remember the special case, whatever adds up to 0 has to be 2 of the same but plus minus, which is what happens here. But hopefully what will happen is you will say, oh, x squared, that is a perfect square. What is the square root of x squared? It's just x, right? So this has a perfect root. The perfect root of this guy is x. We're going to make that a little bit bigger. The perfect root of that guy is x, all right? And then you will look at 49. Does 49 have a perfect square root? It does. What is it? It is 7. And then the other key factor here that you cannot miss is that this has to be minus. And it is. It meets all the requirements. It is a special case. Now that you know the square roots, you just put a plus minus in between them and you have factored it. So the factoring of this is going to be x plus 7, x minus 7. This is really the easiest factoring you'll do, I promise. Do you think you could check it? Yeah, you can always check these, foil it. If you foil it, you're going to get x squared plus, or minus 7x plus 7x, those cancel, minus 49. And so if you foil it, you will see that you got what you started with. Watch. So if we were to check this guy, so we're going to check him over here. We're going to do x plus 7, x minus 7, right? So x times x is x squared. X times negative 7, negative 7x. Positive 7 times x, positive 7x. Positive 7 times negative 7 is negative 49. These guys will cancel out, negative 7 and positive 7. And you get x squared minus 49, which is exactly what you wanted. So this is your answer. So once again, they build a little bit here. The first one was perfect square, perfect square. What's the problem here? 5 is not a perfect square by any stretch of the imagination. But what is our first step always in factoring? Take out your common factor. Do you have a common factor? You do. It's 5, right? And so I'm going to look at these two and say, yeah, I do have a common factor. I'm going to take that out first. Take my 5 out first. What's 5 divided by 5? 1. What's 125 divided by 5? 25. And I have x squared. Now do I have perfect squares? Does 1 have a perfect square root? Yeah, 1 times 1, right? So this guy's a perfect square. That's 1. Does 25x squared have a perfect square root? Yeah, what is it? 5x, right? Don't forget your variable. And is it subtracted? It is. And so this meets all of my requirements. Now, when you have a common factor, that's got to be part of your answer. So you're going to bring that 5 down, leave him on the outside, and then you're just going to plus minus those roots. We're going to say 1 plus 5x, 1 minus 5x. Just leave it in the order it gave it to you, even though it wasn't standard form here. When you're factoring, leave it in the order it gave it to you. All right? This whole thing is my answer. If you were to check it, you would want to foil first, foil your two binomials first, and then distribute the 5 through once you have foiled. And you will get what you started with. Don't let the variables throw you. As long as your variable has an even exponent, listen, even exponent, then it is a perfect square. To figure out what the perfect square it is, you just divide by 2, all right? So if I'm going to look at this, I'm going to check, first of all, do I have a common factor between all of these? Between the numbers, do I have common factors? I obviously at least have 1 because they're even. You can go a little bit bigger than 2, though. 4, actually. 8 won't go into 36. If that had been 32, yeah, it would have been 8. But 4 goes into both of them, all right? What about the variables? We have an x, z, and a y, right? X, z, and a y. So only the 4 comes out. So we're going to take my 4 out. All right. 36 divided by 4 is 9. And I did not touch my variables. No variables came out. 64 divided by 4 is what? 16, right? 1 and 6 leaves us the remainder of 2. 24 divided by 4 is 16. All right. Now I'm going to check, do I have perfect squares? Is 9 a perfect square? Yep. Yeah. Is 16 a perfect square? Yes. Then look at your variables. Look at your exponents. Are they all even? They are. You have perfect squares. Okay. So then we just need to figure out what those perfect squares are. What's the square root of 9? 3. For your variables, the square root is just going to be dividing their exponent by 2. Okay. Because remember, you add when you multiply your exponents. So just cut it in half, and that will be the square root. So if I have x to the 6th, I'm just going to cut that 6 in half to find the square root. So it's x to what power? The 3rd. Z squared, cut it in half. That's why it's just z. All right, because when I multiply x cubed and x cubed, I add those to get the x to the 6th, right? All right, what's the square root of 16y squared then? 4y, all right? That's my first group. What's my second group going to look like? Plus 4y. So once you find your roots, just do a plus minus of them. And whatever you took out to begin with must be part of your answer. So that 4 has to be part of your answer there. Has to be part of your answer. Everybody see? Questions on those? All right, let's try some. Does a squared have a perfect square root? Yeah, it is a. What about 225b squared? 15. It's 15. So you should have gotten, yes, 15b. So you should have gotten a plus 15b and a minus 15b. And no order does not matter as long as you have the plus or minus. You can do either one first. What about 21? What did you need to do here first? Yeah, take the common factor out, which was what? 2. You were left with what? A minus what? 121, right? A squared. Are those both perfect roots? They are. What's the square root of a squared? What's the square root of 121? 11. It should have looked like this. All right. 25. Did you have anything in common? X squared. What are you left with? Minus 16. Are those both perfect roots? They are. So your x squared is going to stay out here. What do you have left? Plus 4 and minus 4, right? All right. Just because you have two perfect roots doesn't mean that you don't take your factor out first, including the last one. These were actually both perfect square roots to begin with, but what do you have in common? A 4. So that 4 actually needed to come out first. You're left with 4x squared minus 1. The 4 stays out here. What's the square root of 4x squared? 2x. What's the square root of 1? 1. There we go. Should have looked like that. If you did not do that, you would have gotten 4x plus 2 and minus 2, and they both are not completely factored because 4x plus 2 has a common factor of 2. And so does 4x minus 2. And so 2 should have come out, which is a 4, right? So when it's completely factored, nothing else can be taken out of your groups. So that's why you always look for your common factor first. The next pattern we're going to look at is perfect squares. We did this in bell work as well. You have a group squared. And what you actually end up with is the first term gets squared, and that represents the first term. The second term also gets squared, and that represents the second term here. And then the middle term is the 2 multiplied together and doubled. And it can be, when you multiply them together, you'll get a positive or a negative depending on what is here. And so you'll notice that this sign follows that positive or negative. These are sometimes a little more difficult to recognize. The other ones are easy to recognize because you're thrown 2 terms. And so you immediately have to think, can I just take out a common factor or is this a special case? Those are really your options with 2 terms. With 3 terms, there is a way to factor these even if you don't remember this. It's just much faster if you do. All right? And so if you recognize that you have 2 perfect squares on the end, the first thing you want to check is, can I take those perfect squares, multiply and double them and get that middle guy? And if I do, then I have this special case. So that's really what you're looking for when you do these. All right, so let's look at these examples. All right, example 4. Example 4 on page 421. So when you get these, you're immediately just going to check them. Hopefully you will notice that you have a perfect square here. Square root of x squared is x. You have a perfect square here. Square root of 25 is 5. Now I will say this has to always, always, always be a plus. Because anytime I'm multiplying the same number, it's either going to be 2 positives or 2 negatives, which means when I multiply them, it has to be a plus. So if that had been a minus 25, it's immediately not a special case. Immediately. You then have to look for factors of 25 that add up to the center guy. All right? which actually this guy wouldn't even be factorable. Sometimes they are. But I do have a perfect square. I have a perfect square. So my next step then is to say, okay, if I multiply these two, I get 5x, right? And then if I double it, because that's my rule, I get 10x. Yes, that tells me it's a special case. All right? So if I take those square roots and multiply them together and double them, do I get the middle term? Yes, I have a special case. And so my special case is just going to be these two roots and then whatever the symbol was here, squared. All right? Now let's say I'd forgotten that. You would say factors of 25 that add up to 10, and you would get, lo and behold, 5 and 5, right? So you would get x plus 5, which is x plus 5 quantity squared. All right? And so if for some reason you don't remember this special case, you can back your way into this one. It's just much faster to remember it. Much faster to remember it. All right, let's look at the next one. Example 5. This one does not look like a special case. Why? I have a common factor. What is my common factor here?
3.
Yeah, 3 goes into all of these. So I'm going to take that out first. 12 divided by 3 is? 36 divided by 3 is? No, you're right. I'm going past it, sorry. And then 27 divided by 3 is? All right. Now, once again, if you forget this rule, you can multiply 4 and 9. I will say if you have huge squares, that's going to be a pain, all right? 4 and 9 is not bad. But if you had a really big square, like let's say we had 36 up front and we had, 49 up in the back there, we wouldn't want to multiply 36 to 49. We would definitely want to remember our special case. But I do have perfect squares, so I'm going to check it. This is a perfect square. What's the square root of 4x squared? 2x. This is a perfect square. What's the square root of 9? 3. All right. It's plus 9, so we've got to figure out that we can potentially have a special case. All right. 2x times 3 gives me 6x. If I double it, what do I get? 12x. That's exactly what I'm looking for. So my answer is going to be, don't forget your common factor that was out here. Then you're going to take these two, 2x and a 3, and that plus or minus is going to be based on that right there. So we're going to say minus, and that guy squared. All right, easy enough. I still want to look for a common factor. Obviously, between the numbers, I don't have one because I have a 1 there. Between my variables, though, I have an x in the first 2, not the last one. I have a y in the first 2, not the last one. I have a z in the last 2. So, no common factors here. All right, so we're going to see if I have perfect squares. Because it's variables, how am I going to tell if they're going to be perfect squares? What do I have to look at? Exponents, what must they be? They must be even. They both are, so this has perfect roots. What's the square root of x to the 6th, y to the 4th? X to the 3rd, y to the 2nd. All right, 16z squared. Does that have a perfect root? Yeah, it's 4z. All right, so I have perfect roots. Now I'm going to check to see if they make it to the center guy. So I'm going to multiply these. I get 4. And I'm just going to go in order. X cubed, y squared, z. And then I'm going to double it. When I double it, I get 8. X cubed, y squared, z. Is that my middle term? It is. Everybody see that? So I have a perfect square. All right. So my perfect square is going to be, I didn't have a common factor, so we'll just start right with this. This is my first term, x cubed, y squared. This is my second term, 4z. Is it going to be plus or minus in between there?
No.
Minus. Why? That guy right there. Minus. And don't forget, it is squared. Yes, it is. So the first one is a perfect square. You should have said yes. We know the first and last are perfect squares, but how do you know this is a perfect square trinomial? Right. Square root of x is x. Square root of 9 is 3. 3 times x doubled is your middle term. So this is the reason why. Your middle term is 3x doubled. Right? What about the second one? Yes or no?
No.
No. Why not?
Because the y is not like on the x squared y.
Right, so for this one, we have a perfect square right here. The problem is that this y is not a perfect square. So you can stop right there. We have to have a perfect square there for this to work. This guy worked, right? We have a perfect square here. And if you take 4 and double it, you're going to get your 8. The problem is this little y up front. Now, I can do something. I can take a y out, right? But then what does that do to the last guy? He's no longer a perfect square. He's just 16y. And so it causes problems across the board, even if I take my common factor out, right? All right, so for these last three, we had to actually factor them. This first one, what's my square root of x squared? X, what's my square root of 9? 3x doubled does give me the 6x. This is a positive, so we're good to go. You should have had x what? Plus or minus? Minus 3 quantity squared. All right, next one. Square root of a squared is a. Square root of 25b squared is 5b. If I multiply these two together and double it, I get my 10b, which is what I want. All right, or 10, sorry, ab, that works. Put a little a there. All right, so I have a and 5b. Am I going to plus or add or subtract those? I'm going to subtract them because of that middle term. So you should have gotten a minus 5b quantity squared. All right. And then 23. Square root of 9x squared is 3x. The square root of 4 is 2. If I multiply these, I get 6x. Double them, you get your 12x, which is what you want. This is an addition, so we're good. So I'm going to take my first term and my second term. For this one, you should have said plus 2 quantity squared.